We are live on platform and YouTube and in class, of course. So yeah, I guess we can go ahead and start the class. The first thing we want to do is to go back to the example problem that we didn't work on for chapter 4 last week. This was where we left off last week, and I forgot to finish it off on Tuesday. So we are going to start working on that one. And yeah, let's see. How much did we cover? I think we talked about, we at least started working on it, right? That was the idea. Let me go through the problem again. We are supposed to consider a square flat plate at 0 incidence angle to a low speed incompressible flow. The length of each side is 4 meters. Assume that the transition number is 5 times 10 to the power 5. That the free stream properties are those at the standard sea level. Calculate the friction drag on the flat plate when the free stream velocity is 20, so 3 20 meters per second. V infinity, V infinity is 40 meters per second. And the idea was for part C, we are going to find the relationship between drag or drag force or drag coefficient. Drag force, the friction drag, to V infinity to the power n. You essentially want to find this n. Okay. When it comes to this type of problems, the first thing you always want to do is to determine whether the flow is turbulent or laminar, or if it's turbulent or laminar, if it contains both type of flow, where does the transition start? So you essentially want to find the critical length. How do we calculate the critical length? We essentially use the Reynolds number, the transition Reynolds number, 5, 10 to the power 5. So for part A, you want to calculate the critical Reynolds number, your critical length. Your critical Reynolds number is rho infinity, V infinity, L divided by mu infinity. L or C, let's call this C. This is your chord length. I'm sorry, X critical. X critical, right? So we have the Reynolds number, we have the rho infinity. These are the standard sea level properties, which you can get from the tables in the book. For density of air, we have 1.23. For viscosity, we usually have 1.789, 10 to the power -5. Velocity, 20 for part A, 40 for part B. So, and we also have the Reynolds number, so we can find the critical length to be, I think you guys calculated this part on Thursday, right? So we already have this value for part A, critical Reynolds number. Is this critical Reynolds number smaller than the chord length? Yes, like the chord length is 4 meters, right? Let me double check. Yes. So this is smaller than 4 meters, which essentially means that the transition happens, we are going to have both regimes here, laminar and turbulent. Okay, so how should we deal with this problem? Let's find the turbulent drag first. Let's actually, this is your flat plate. This is how the boundary layers are going to look like. The transition should happen here. It is not up to scale because this critical is 0.36 and the whole thing is 4 meters. But you get the idea, right? The transition happens here. The idea was for the turbulent drag, let's call this part A, part B. The first thing you do to calculate the turbulent drag is to assume the whole plate is turbulent. So D, let's call this D of T of A plus B. That's the first thing you want to calculate, right? You're going to assume the whole plate is turbulent. And turbulent, the drag force in general is your Q infinity multiplied by your span multiplied by your friction coefficient. You're talking about the friction drag, so we have to use the friction coefficient. What was the friction coefficient formula we had for turbulent boundary layer? What was it? .074 divided by the Reynolds number of L to the power 0.2, right? For friction coefficient, C of F. What do you have in your notes? Why are you so confused?
I was just trying to find it.
Oh, okay.
Two of them. One that's like you did, and the other one is the 0.0592 over Reynolds number to 0.2.
Okay, what was the difference between the two?
One's a CFX, and one's CFL.
Okay, so the other one is. Okay, let me ask you this then. What is the difference between the two? What does it mean?
Critical and full. Well, this one's over the whole core length that we have up there, right? So the one that's the 0.0592 is over just a section.
The 0.05 whatever is just a point value, friction coefficient at the point. This is the average value, so the total value. So the friction coefficient for this plate, which has this length, right? If you want to calculate the average value up to a point, or the total value up to a point, you have to use this formula. If you want to calculate the friction coefficient just at one point, you have to use the other formula. The difference is between a point friction coefficient and a total friction coefficient on a plate, on an airfoil. Okay, so next step is to calculate the Reynolds number at L. We have rho infinity, we have V infinity, we have the L, which is 4 meters, or C, we call this C, divided by mu. We have all of these values. Your Reynolds number will end up being 5.5, 10 to the 6. How can we calculate Q infinity here? One half rho V squared. We have all of the parameters. Q infinity is going to be 246 newtons per meter squared, or pascals. And what about the span area? based on the information that is given to us, this is a plate that is 4 by 4. So the span area is going to be 16 meters squared. That's 4 by 4. So we have all the numbers we need. You just plug in the values to calculate the drag, the turbulent drag, assuming that the flow is turbulent all over the plate. Okay, and that value is going to be 13.07 newtons. Okay, what is the next step now? We have assumed that the flow is turbulent all over this plate. But we already know that that is not the case. In part A, the flow is laminar. In part A of the plate, the capital A. So what should we do? So what Trey is telling us is to calculate the laminar drag here and subtract this turbulent drag that we have calculated, d of t, let's call it d of L. But what does it give us? It essentially is going to give us the, it doesn't have any physical representation, right? You're just removing the laminar. And you cannot just remove the laminar part because it does exist. It is generating some drag. So in this assumption, this calculation, where is the unphysical part that doesn't really exist on the plate? Which part doesn't exist in this calculation, in this turbulent drag calculation? The turbulent drag in part A, right? Part B is already turbulent, right? We can see that. We have calculated, we know the transition happens. But part A is laminar. So the turbulent, that portion of the drag force here that is there because of the turbulent assumption in part A is the unphysical part. We want to remove that. Does this make sense? We talked about it last week as well. So what should we do? We have to calculate how much is the contribution of that unphysical portion and just remove it, right?
You calculate turbulent force on A and then subtract it?
That's it. So we don't calculate we should calculate the laminar drag eventually, but we assume that this is a separate plate, this part of it, part A, right? Which is turbulent, completely, fully turbulent. Then they calculate the drag force for this plate, right? And then subtract it from the total turbulent drag here. That will give you only the drag force, the turbulent drag force in part B. Does this make sense? Okay. So let's do that. So we are looking for, and this is still part A, we are looking for turbulent drag of section A of the plate, right? Everything here is going to be the same except for the Reynolds number. Essentially, not everything. S is going to be different as well. Reynolds number is a function of chord length. In this new plate, your chord length is 0.36, right? 0.3636. Yeah, that's the assumption. We are taking only that section. And your span area is going to be 0.36 multiplied by 4. Okay? Is this clear? Okay. So if you plug in those values, you're eventually going to get this number, 1.92 newtons. And then again, we are looking to get the turbulent drag in part B, where the flow is really turbulent. Yes.
So instead of calculating the Reynolds number again, can we just assume there's 5 times 10 to the fifth as we calculate the excreted
Yeah, definitely. That's the idea. Yeah. That it should give you the same number, right? So we want to find the turbulent drag in section B of the plate where the flow is really turbulent. We have this calculation. We have calculated this drag with assuming the flow is turbulent all over the plate. Then we have calculated the turbulent drag only for part A. Part A, which starts from 0. And 13.07 minus 1.92 should give you 11.15 newtons. So turbulent drag's contribution is going to be 11.15 newtons to the whole thing. This is the contribution of section B of your plate to the friction drag of the plate. Okay. What is the contribution of part 1? It's the laminar flow friction drag. Okay. So we have to use this formula again. Instead of turbulent, we want to find the laminar flow drag, Q infinity, S, CF. And the CF here is the laminar CF. What is the formula for laminar CF? Exactly, 1.32 over the square root of Reynolds number. And what is the Reynolds number here? We are going from 0 to the critical point. So Reynolds number is 5, 10 to the power 5, right? This CF, 1, 2, and then the span area that is covered by the laminar flow. It is 4 multiplied by your critical length, 0.3636. Plug all of those numbers in. Your friction drag due to laminar flow is going to be equals to 0.67 newtons. Total friction drag, just have to add these two, 11.15, 0.67. So total friction drag of part A is going to be, so I'm just going to give total friction drag of part A is going to be 11.15 plus 67, which is going to be 11.83, right? $82. Why did I do that? Okay.
Just to recap, we found the power force over A plus B, assuming it was entirely turbulent.
Yep.
Then we found drag force of A, assuming it's turbulent.
Yep.
Then we did A laminar, and then we came to our final drag force.
That's it. So do the exact same analysis for part B. The only difference is that your velocity is going to be different, which means that your critical length is going to be different. So let me give you the values. Part B. Okay. The values, your critical. Okay, let me ask you this. We are having a higher velocity, 40 meters per second. What should happen to the critical length? Should be half, exactly. So we're going to have 0.1818 meters. Everything else is essentially the same. the equations are all going to be the same, just the numbers are going to be different. So I'm just going to give you the final drag of part B, which what was that? What was it? It's the number I have here is 43 newtons. So either my number is right or yours. It is a lengthy process, yeah. None of you have passed heat transfer, have you? You have. You didn't do this in your heat transfer? Who did you have your heat transfer with?
Chen, we were done like Reynolds number calculations and those kinds of things. We didn't go for drag.
Oh, okay. But you calculated the friction coefficient, right?
Yeah.
Just one
We
step.
always assume the flow was the same in there with a circular tube because it has a different Reynolds number cutout.
But that's so you didn't do any external flow.
No.
Okay. Okay. Yeah. So what should we do for part C? We want to find this value of N, right? The power here. We have the dF for part B, which was 43 newtons. We have, so 43 is proportional to V infinity, 40 to the power N. We have this value. And also, we also have 11.82 proportional to 20 to the power N. Pardon me?
They're going to be different values of them.
No, they have to be the same, yeah. But this is, you cannot do anything with the proportionality. You have to convert this proportionality to an equality, right? How do we do that? We essentially divide, and this is something that you need to keep in mind in your future. Like, if you had this proportionality and you had 2 points in your system, if you divide them up, you are essentially removing all the constants that you don't know here, right? Because the constants are supposed to be constant for both of these. So if you just divide the two proportional relationships up, you're removing all of those constants. Does that make sense? Okay. So 40 divided by 20 to the power N. And then I'm sure you can definitely know how to calculate N here. There are many different methods you can use, but simplest of which is just taking the log of both sides and so on and so forth. And eventually your N is going to end up being 1.87. Is there any questions? Have you guys submitted your homework? Is it due? Oh, it's due Tuesday, right? Okay. Okay.
If we had a question like this on the exam, would we have to do the two different velocities and all that, or would it just be like find the drag?
I don't think you're gonna get a question like this in an exam. I don't think so, because it is very aerodynamics related, not that much flight mechanics, right? And that's actually the main reason I skipped over in the previous lecture because I didn't want to focus on it, but you guys asked for it, so decided to go solve it. But if you do so, you will only get it for one velocity. So I would just ask you to calculate the drag, right? Or if the question has many parts, essentially I'm not gonna ask you to redo the whole thing. It's gonna be a different thing that you need to do. Does this make sense? Yep. You'll probably actually, we can relate it to flight mechanics somehow. Eventually, I can give you a wing and ask you to calculate the total drag for it. One part of it can be friction drag. Yeah, that's a good idea. Thank you for the idea. So you have him to blame if you. Okay, so let's go back to the discussion for chapter 5. I think we stopped at, where did we stop at?
We had just gone over critical.
Okay, so we talked about CP critical. At this point, hopefully you know what the critical CP and critical Mach numbers are. Just to make sure we are on the same page. Who can tell me what is the critical Mach number? No. What happens? What is the significance? What happens when you reach the critical Mach number?
Oh, that's where a portion of the flow over the wing.
Exactly. So that's essentially this not just a portion, a point. Okay, becomes sonic. So the critical Mach number is the Mach number at which you will get the sonic velocity at your minimum pressure point, which is supposed to give you the highest velocity. Okay? And so M critical, you will get sonic velocity at CP mean, which is going to be your CP critical pressure coefficient. So the question is, what is going to happen if you increase the Mach number after increase the Mach number after you have already reached the critical Mach number, and your Mach number and infinity is still lower than 1. So you're essentially between the critical Mach number, or I can rewrite this to make it a little simpler. M critical is smaller than your M infinity and smaller than 1. What is going to happen? On the airfoil, you are going to get, as Lawson mentioned, and when this situation, you are going to get a portion of your flow over the airfoil or whatever that is, the flat plate, is going to be larger than 1. Okay. What if we increase this value even further? What do you think we are going to see? So at some point, what we are seeing here is a very weak region of supersonic flow, right? Meaning that the supersonic speeds are not that strong, I mean like 1.1, 1.05, right? And I assume if you increase this Mach number a little further to get closer to 1, this supersonic region is going to become stronger, meaning that you're going to get higher velocities, 1.2, 1.3, whatever, right? It's going to get stronger. So what are we going to see here? We have a region of supersonic flow on the wing, on the airfoil, and it is comfortably supersonic, so it's not in the transonic region anymore, what are we going to see? Shock waves, exactly. So we're going to see local shock waves. M larger than 1, M smaller than 1 after the shock. And you will probably see flow separation here as well. Okay, so there is a point after which you're going to get a shock wave. Well, what is going to happen, or what is the difference in flow properties, in air properties, in flow properties, right? Before and after the shock wave. Your velocity is going to decrease. What is going to happen to pressure? Increase, right? That's what happens after the shock wave. So this, let's call this point 1, region 1, region 2. Your P2 is going to be larger than P1. So there is a point after which you're going to get a huge pressure jump because of the shock wave, which means that you're going to have a very huge pressure gradient, adverse pressure gradient. Okay? So what does it mean for the drag force? Drag increases rapidly, right? You will essentially see a jump in drag because there's a point after which you're going to see a shock wave and your drag is going to increase. So if you want to look at a pressure coefficient distribution for this, this is how it looks like. And we went from positives to negatives. On top, this was the distribution. Then you're going to see at the shock wave, you're going to see a huge increase in the value of pressure compared to the P infinity. So when you are going down here on CP versus whatever, versus X, we are becoming more positive. P is getting closer or larger than P infinity, right? That's the conventional, that's the normal way of talking about pressure coefficient. So in this region, we're going to have locally supersonic flow, and here we're going to have locally subsonic flow, and so on and so forth. It doesn't necessarily become positive, but the point is, there is a huge jump, which again, very high adverse pressure, very high drag coefficient. So this point, at the exact same point, at the exact same Mach number, when this shock waves starts to appear, that exact Mach number is called the drag divergence Mach number. Which essentially means that we are talking about a region at which the drag is going to diverge. What does it mean? It means that it is going to increase rapidly. So let's say if you have D versus M, what you're going to see, let's do CD, drag coefficient. What you're going to see is that you are going to see a fairly constant drag coefficient until you get to this critical Mach number, and then it will start increasing until you get to the drag, I'm going to call it DD, the drag divergence, and afterwards you're going to get a very huge increase. So drag divergence, it happens because shock waves start appearing on your airfoil, on your wing, whatever that is. And we're going to have flow separation afterwards as well. So drag divergence. And drag divergence is between, again, I'm going to call it DD, is always between the critical Mach number. One critical Mach number is usually around 0.7, drag divergence is usually around 0.8. Depends on a lot of things, but that's the usual number. That's where your transonic flow stops. Okay. Is there any questions? What are the methods? If there, is there any questions? I didn't. No. Okay. What are different methods that we can use to mitigate this drag divergence, to delay it or just remove it?
What if we make the entire aircraft go faster than speed sound?
So supersonic.
Yes.
Okay. But you're essentially going into another region, right? Let's say you have to fly for whatever reason. You have to stay below the supersonic. But I mean, we're going to talk about the supersonic as well in a bit, in like 5 to 10 minutes. That was an interesting perspective, though. Let's say we want to keep the flight velocity at this region, okay, at the drag divergence region, but we want to prevent the drag divergence. We cannot just prevent it. It will happen eventually because the shock waves will eventually appear. Flow separation will happen. There's nothing you can do about it. But what if, let's say we want to fly at Mach 0.8 and but we don't want to see the drag divergence?
Is there any way we can decrease the cross-sectional area to like allow the flow not to reach the critical max?
Then you are also using that. You are also decreasing the cross section, but you're essentially affecting the whole drag coefficient, right? The whole drag force, not just the drag coefficient, right? And also the lift coefficient. But reducing cross sectional area, yes.
You make the airfoil thicker, wouldn't this critical point or the drag divergence point happen earlier in flight?
Okay, that's bad though, isn't it?
Well, not passing on your like your rate of acceleration that happens like earlier in flight, so that when you're cruising, you don't even come close to your drag divergence.
Okay, you are making a good point. If you do that, if you make your airfoil thicker, what is going to happen is you are going to get to the drag divergence sooner. But the point is not just like delaying the drag divergence. We want to get lower drag at a higher velocity. Does this make sense? So if you do that, you're going to get higher drag at lower velocity. You're essentially doing a 180 degrees turn, right? And yeah, I assume dealing with a situation like you mentioned is going to be easier because you can predict the drag. You can predict a higher drag, but you're going to need a higher lift. You're going to need a higher thrust, right? You're going to need a higher thrust in general. So you're going to need a stronger jet on your aircraft or whatever that is. Yeah, exactly. So if we do a thinner, flat, more flat, specifically more flat airfoil. So the first thing is to do a thin airfoil. If you do a thinner airfoil, you are going to delay the drag divergence a little bit, which essentially means that the drag divergence is going to happen at speeds closer to the supersonic speed. You're making the transonic region a little smaller. There is another solution to this, which I assume none of you can come up with because it's a new generation of airfoil. So these are called supersonic critical airfoils. These are essentially airfoils that look like this, are flat on top, as flat as possible, and usually look something like this. NASA's what aircraft? I'm not sure. I'm not sure, but I can like look it up for you. Looks like what? Kind of like, if I guess so. Yeah, but so the first use of this thin airfoils was on Bell X-1, which I'm hoping you're familiar. This is a very famous aircraft, not a very practical one though. And the first use of this one was on F3. And what is going to happen to your CP versus chord length is that you're going to get a more something like this, right? So a more flat pressure distribution. Yes.
Do these same conditions happen on helicopter blades or rotorcraft blades?
Which same conditions? This condition? Yes, definitely.
Okay. Do the same solutions like their airfoils or supercritical airfoil blades?
So there are a lot of other considerations that come into play when you're dealing with a helicopter blade or blades in general, right? You usually have to deal with this type of blade, this type of condition, and I have to think about it whether these solutions apply, because there are other considerations that you have to make, right? But I would assume yes, it would apply, right? Yes.
When will the helicopter, the farther out the blades are, those hit supersonic first rather than closer in? So then you have to have consideration for that.
Why is that happening though?
Because of the radius increases faster.
So yeah, and I assume you're interested in helicopters because you're just talking about helicopters in your aircraft systems course. But there's no but, right? I assume that you're interested because okay. Any other questions? That's okay. So we are doing a two-dimensional analysis here at this point, right? What you're doing is a three-dimensional analysis, right? So don't apply this knowledge here to your helicopter knowledge. That's the first thing. But let's answer your question. Let's see if you have any ideas. Does the tip of a helicopter blade experience more, or let's make it a more general, a rotor blade, right? It can be a jet, a propeller for a jet or whatever, right? Does the tip of that blade experience more drag than the place that is closer to the center of your rotor? Tentatively. Okay. Can you elaborate?
Since it would be moving faster than the inner part of the rotor, I'm inclined to say yes. Part of me also wants to say that if the tip of the rotor is breaking the speed of sound, that means the closer you go into the rotor, the slower it's rotating. So that we would have a moment like this where your Mach number is critical, and that part will be experiencing more drag than the tip of the rotor.
Okay, so you're talking about an interesting phenomenon that is happening, and we're going to talk about it in a few minutes. if we had the time. But in general, the drag is a function of your velocity, right? Because of the dynamic pressure. Any force is a function. I mean, lift, drag, all of them are a function of your velocity, right? So if you increase the velocity, you're going to experience more force. That's something that's happening. Your linear velocity. If you increase the linear velocity, you're going to experience higher force. And the drag force, the drag coefficient, though, is going to be a different thing. You have to make sure you understand the flow regime that is happening locally on that blade, okay, as Lawson mentioned. And we're going to see, so we have the distribution of drag up until M1. So it will essentially reach a climax or reach the highest value at 0.1 or close to 0.1, as close to 1, not 0.1. And the next part of this lecture is going to focus on what is going to happen afterwards, right? Supersonic conditions. I really like the fact that you guys, aerospace students in general, are very involved in class. Ask questions. I really like that. You should come sit in my fluid mechanics class. It's dead. I mean, I know it's going to be on YouTube. Wow, but it is dead. So I hope they, pardon me? They're all mechanical, yeah. I am a mechanical engineer, right? Also, it's VAT. We are all mechanical engineers. So, yeah, so keep it coming. Probably like 80% of them, I don't know the answer, but that shouldn't discourage you or me. I'll try to find the answer for you if I didn't know. And sometimes we can come up with the answer ourselves. Okay, so let's continue the discussion. Let's talk about the supersonic flights a little bit. So supersonic flights, essentially Mach number larger than 1, which means that your velocity is larger than the speed of sound. And we all know that when this happens, you're going to experience shock waves, right? You've seen this many, many times. We have heard about it many, many times. But why do the shock waves happen? What is the mechanism behind shock waves? Why do we experience shock waves?
The body's going so fast, it compresses the air in front of it and has to move out of the way, right?
Exactly. So that's essentially it, right? But to make it to explain it a little in more detail, let's just start. This is a very famous example. So whenever they want to talk about shock waves or pressure waves or whatever, they will give you this example. So you may have heard it before. You may hear it again later. So yeah, let's think of a beeper. Okay, a beeper that is generating sound waves. And we all know that the sound waves move with the same speed in all directions, right? So they're moving in the spherical direction. Let's say at time 0, this beeper, this point beeper generates a beep, right? And it is moving at velocity v, which is smaller than the speed of sound, right? What is going to happen at time t1? This beeper has moved v multiplied by t1, right? That's the distance it has moved. How much the beep sound, that sound wave, has moved? Further, exactly, because this velocity is higher than the velocity. So it's going to be a sphere, and we're dealing with two-dimensional thing. So the distance the sound wave has moved is going to be, the radius of the circle is larger than this, okay? Subsonic speed, pretty understandable. But what is going to happen when this beeper is moving at a velocity that is higher than the speed of sound? It will be outside of the circle, right? After time t1. What does it mean? It means that the upcoming flow here, the air here, didn't know the beeper existed. It just suddenly appeared, right? Because this beeper, right, is going to be felt in this direction, right? The disturbances this beeper has made is going to be felt in this circle, in this sphere, but it's already outside the sphere after time t1, right? So the air is not going to see what is coming. That is why you're going to experience something called a Mach wave. So the air upstream, this beeper doesn't have any idea this beeper exists, and the air downstream it has already already hit with it, but didn't know it is coming, right? That's why the properties are going to change before and after this Mach wave. Right? So it is going to create a disturbance, and that disturbance is going to be tangent to the sound wave. Does this make sense at all? Okay, so we have AT1, we have VT1, and this is for a beeper. Well, why do we have this? Why do we have this Mach angle? Let's say this beeper is beeping. In real case, this disturbances is being made every second, right? There's no. So let's say we had another disturbance here. It has moved AT1 like this much, right? This much less. The circle that it has made, it has moved this much less. So you're going to get this circle, and then you're going to get this one. You're going to get this one, right? Does this make sense? So all of these are going to create this Mach angle, Mach wave. Okay. This Mach wave is this clear, right? A compression of all of these sound waves together are going to create the Mach angle. So flow here has already felt the presence of this beeper. Flow upstream has not, doesn't know what is going to hit it, right? And then we can create this angle mu. We can measure, not create. We can measure this angle mu How can we measure this angle? Sine of this mu is equals to what? Is equals to this value divided by this value, right? Okay, so AT divided by VT. Y divided by R. T's cancel out. And the Mach angle, or mu here, so this mu refers to Mach angle, is arc sine of A divided by V. Any beeper-like object is going to experience the same thing. It's going to experience a Mach wave. This is not a shock wave yet, right? It's just a Mach wave. So any needle, anything that has a zero thickness, right? is going to experience a Mach wave. And we can calculate the Mach angle using this formula. So this is a Mach wave. What if the thickness of this beeper or the object that is flowing through air is not zero? Yes.
Is that A, B?
Yes. Or 1 over m, right? 1 over the Mach number. That's the definition. What if your object doesn't have zero thickness, which is the case, right? Zero thickness. Pardon me? Oh, you're talking about the Mach wave. So what you're saying is that if we have an object like this, the Mach angle is going to be smaller. It's actually going to be the opposite. So because you're essentially pushing the air a little bit, right? And that the difference between the properties here and here is going to be stronger because you have a bigger object that is hitting the air, right? So the property change is going to become stronger, and you're going to experience a shock wave instead of just a small Mach wave, right? Does this make sense at all? Okay, so, and the angle, the shock angle, beta, is usually bigger than the Mach angle. So let's say we are dealing with a slender object. You're gonna see a if you're not clear of why this angle is going to be bigger, think about it this way. Let's say I have this slender object that is moving through air with higher speeds higher than the speed of sound, right? The effects this slender object with this angle is going to have on the air can be felt here, right? Which means that we're going to get a shock wave here. What will happen if I increase the angle? The distance the effect is going to be felt at is going to stay the same, right? So whatever value that is going to be increased because I'm increasing its value. So if I have a bigger angled, a slender object, your shock wave is going to move further away, right? Because this distance is not going to change for the same velocity. Okay?
You think about it like dropping different sized rocks in water. Like a larger rock would make a larger ripple.
Yeah, I mean, the radius of the ripple is going to be larger. Yeah, that's the idea, I guess. Yeah, it is pretty similar, I guess. Okay, is there any questions? No. Yes.
The size of the wave affect how we interpret it as far as sound-wise. Like the bigger shock waves that happened longer ago sounds different than the ones that more recent.
Bigger shock wave that happened.
I've heard anecdotes from people in the armed forces about a bullet whenever it's passing by you.
That's the Doppler effect. The Doppler effect.
No, as far as like distance from it, like if it's here versus like up here, it sounds different, but not forward to backward, just up and down.
Oh, okay. That's not a shock wave though. That's just a regular sound wave that is getting. So I'm thinking about it this way. We don't have any perfect sound propagation, wave propagation in the world, right? Because we have a lot of losses. Right? We will always the sound is moving through the air molecules hitting each other, right? We are always assuming that this is a perfect hit, right? It is always moving. 100% of energy is being moved from one molecule to the other one, to the other one, to the other one, right? But this is not the case, right? You're losing some energy. So the sound you're going to hear from 1 meter away is definitely going to be different from the sound you are gonna hear from like 20 meters away. Okay. So I assume that's something that should definitely happen. Yeah. Any questions? Okay. So moving on, this shock waves. Let me actually tell you about this as well. We have. Let me ask you. Let's actually do a small brainstorming thing. Let's say the idea was the angle of attack is 0, right? Up until this one. What's going to happen to us if the angle of attack is not 0? What is going to happen? So if the angle of attack was 0, so we had this flat plate, you would have seen an oblique shock wave, right, on both sides. But what will happen if the angle of attack is not 0? A larger shock wave? What does a larger shock wave mean? Because both of you have mentioned this, but I don't know what a larger shock wave is.
But since your cross-sectional area really where the flow is larger, you would have shock waves start up here, then one at the bottom, so it'll be bigger than just the long point.
Oh, you're talking about the length of the shock wave here, right? It is going to be a bigger shock wave. Is that what you're saying?
Yeah, it's just like one hits the nose of the angle of attack, and one hits the bottom, so it'd be bigger cross-section.
So you're going to see something like this. Is that what you're saying?
But you also have the effect on the underneath of this plate too.
Okay, so how is it going to look like? No, it is not an interrogation. You don't have to, I don't. The reason I'm asking is because I don't understand what do you guys mean by a larger shock wave. Yes.
We have like a larger angle on the bottom and then a smaller one on the top.
Is that what you mean by a larger shock wave? A larger angle? Okay. So let me make it clear for myself. So a larger shock wave is essentially going to look like this. This is a smaller shock wave. This is a larger shock wave. So a larger, is that what you mean? Okay. Oh, that's good. I didn't know. So what Witt is telling us is that we are going to get a shock wave like this and a shock wave like this here, right? Okay. No. No. But no. Two shock waves. Let me try to help you. It is good though, because you will always remember these phenomena. Okay, it looks like so. So we are not. So what you're saying is that we are not going to have any shock here, right? We are going to have just a shock here. But so what is going to happen? So this is essentially physically impossible because you are saying that the presence of this flat plate, the bottom half of this flat plate, is never felt by the air, which is like impossible, right? There should be some sort of interaction. But let's think about it this way. Let me help you with your thinking a little bit. So the flow on the bottom is getting compressed, right? So the sound waves are essentially accumulating on the bottom, right? So on the bottom, we will definitely see a shock wave. Okay, that's for sure. That's what we will see. I don't know how large or how small is going to be the angle of attack, the shock angle. It will definitely depend on your flow velocity. This is V infinity. And it may also depend on your angle of attack. Okay, a shock angle. Because we are getting flow is getting compressed, so the sound waves are going to get compressed, right? The shock, the pressure waves essentially. We're not going to call them sound waves anymore. But here on the top, the flow is being expanded. Okay, it is not being compressed. So the pressure waves, we will have millions of pressure waves, but they are not being compressed. They're actually being pushed away from each other. So we're going to get a new phenomena here, which is called an expansion wave. Expansion waves act the opposite way as the shock waves. So you're going to get a lower velocity after a shock wave. You're going to get a higher velocity after an expansion wave. You're going to get smaller pressure. Yes. No. So the idea is after an expansion wave, you're going to get higher velocity. What does it mean for pressure? Lower pressure. So your pressure is being lowered on top, higher on the bottom. So your lift is going, yes. You have to include the effects of pressure waves in your analysis somehow. The air is being expanded, right, on the top, right? So it is from the same nature. Pressure waves are going to get further away from each other because of the expansion. Okay. And then when this flat plate is passing, whatever remains here has to be the same velocity as V infinity. So at the trailing edge, we have to get the opposite phenomena, right? Because when the flat plate is not there, its effect shouldn't be felt, right? That's the idea. So since a shock wave is the opposite of an expansion wave, when you start with a shock wave, you're going to end up with an expansion wave at a trailing edge. When you start with an expansion wave, you're going to end up with a shock wave at the end. But predecessor, how do see here? The expansion wave is happening after the shock wave. Here is happening before the shock wave. It depends on what is happening to your flow. Right, on top here, your flow is expanding. You're gonna get an expansion wave. Here, flow is being compressed here on the bottom. You're gonna get a shock wave. But here at the end, at the trailing edge, right? Since you have a compressed flow and you want to get to the regular flow V infinity condition, you have to expand the flow. You're the expansion wave. Here, your flow was already expanded. You want to compress it. You can go, yes.
Yeah, how does it go from expansion on the top to compression on the bottom? What causes the change?
The continuity, right? So flow wants to get the air stream is coming at V infinity, and here the velocity of air stream has to be V infinity. So the situation is going to force that expansion wave. Does this make sense? Okay. Then the question is, how do we? One thing that I forgot to mention. Because of these shock waves, what you're gonna experience a. Let's talk about this slender object. Your pressure distribution on top and the bottom is going to be affected. It's going to change, right? Because of the shock wave, right? Because the pressure is changing because of the shock wave, right? So this distribution is going to change, right? And we, on this type of object, on any object, there is one component of this pressure in this direction, right? This pressure force in this direction, which is the direction of your drag force. So these shock waves themselves, the supersonic conditions themselves, are going to cause a form of drag that is called the wave drag. And it is called wave drag because it is generated by a pressure wave, right? A compressed or expanded pressure wave. Does it make sense? So it is in nature, it is the same as pressure drag, but it's called the wave drag because it is there because of the presence of shock waves. How do we calculate this? I'm just going to give you a formula. Your wave drag coefficient, let me write the name in case you don't hear me, wave drag. Your wave drag coefficient is 4 alpha squared, a square root of m infinity squared minus 1. Square, yeah. And we can actually calculate the lift coefficient during a supersonic flow using an equation that is very similar to this equation, 4 multiplied by angle of attack. We don't have the squared here anymore. The square root of m infinity squared minus 1. Alpha, angle of attack, alpha squared. 4 alpha squared, yeah. Okay, the last thing that remains from this chapter is the induced drag. Is there anyone who can tell me what the induced drag is? I don't think we're gonna, I was planning to finish this today, but we definitely cannot finish it in 2 minutes. So I'm just gonna ask you this. What is the induced drag? Or why do we have the induced drag? You went over it in your aerodynamics, so you don't know this. You don't have to know this. But the rest of you, drag to due to lift, right? Why do we have that? Because of a pressure difference. How does pressure difference between bottom and top is going to generate drag? You are missing one essentially word, one phrase. No. No. It is an independent form of drag that is a function of your lift, actually. So when you move from a two-dimensional airfoil, which is considered to be an infinite wing, right? When you move to a finite wing, you are going to get tip effects, right? So there are some pressure are going to leak to the top from the tips. This phenomenon is called the downwash. Exactly. So because of that downwash, you're essentially losing some pressure differential between the bottom and top. You're losing some lift, and you are creating some drag, which is called the induced drag. We will talk about induced drag in the next lecture, and that will be the last discussion we're going to have on aerodynamic shapes. There are some parts of chapter 5 that remains that I'm going to, you have to, like the swept wings and all of those things, I'm going to assign them as a homework problem. So essentially you have to read that part of the book and give me a summary, like a one or 2 page summary. And that will be a 1 question in your homework too, which is going to be posted in a week or 2, I'm not sure. Yeah, that's it for today, and have a good rest of the weekend.